Good morning, everyone. I'm Shirantaya from the Department of CSE AML Section C, first semester. Today I'll be representing on the topic of Eulerian graphs and their properties a comprehensive review. This presentation is a part of the subject of essential problem solving, and my aim is to show how a simple real world problem leads to one of the most fundamental discoveries in graph theory. Introduction to the graph theory. Before we dive into the Eulerian graph, let's first understand what is graph is. A graph G is made up of a set of vertices. We can think of them as points and a set of edges that connect those points. The degree of a vertex is simply the number of edges touching it. If that number is even, we call it an even degree vertex. If it is an odd, we call it an odd degree. A connected graph means that can travel through any vertex to any other vertex through any edge. We also use terms like walk, trail, and circuit. A walk allows repetition of edges. A trail does not repeat edges. A circuit is an closed trail. It starts and ends at the same vertex. These are the basic building blocks of understanding Eulerian graphs. Rosenberg problem. The story of Eulerian graph begins in 18th century with the Konsberg bridge problem. The city of Konsberg has 7 bridges connecting its land areas. The people wonder how can we walk through the city across each bridge exactly once. In 1736, the great mathematician Leonhard Euler represented his as a graph. Each landmass became a vertex, and each bridge became an edge. This proved that such a walk was impossible, and that discovery gave birth to a graph theory itself. This is one of the first examples of using mathematicians to solve a practical routing problem. Defining Euler path and Euler circuits. Now, what exactly are paths and circuits? An Eulerian path is a path that transfers every edge exactly once. An Eulerian circuit is a closed path that starts and ends at the same vertex again, covering every edge exactly once. So in short, a path covers all the degrees once, while a circuit does not the same but returns to the start. So Eulerian path, a trail that visits every edge of a graph exactly once. Different vertices are the same if it's an circuit. Eulerian circuit means a circuit that visits every edge of the graph exactly once. It's at the same vertex. Eulerian graph, a connected graph that possesses an Eulerian circuit. It is nothing. Euler's theorem, the main condition. Euler's theorem gives us the precise condition for when a graph is Eulerian. It says that a connected graph has an Eulerian circuit if and only if every vertex has an even degree. Why even degree? Because in Eulerian circuit, every time you enter a vertex through one edge, you must leave through the another. That means every edge always come in pair, making the degree even. In Coenberg graph, 4 vertices has odd degrees, and that's why no Eulerian circuit could exist. Semi-Eulerian graphs. Now, if if a graph has exactly 2 vertices with odd degrees, it's a semi-Eulerian graph. That means it has an Eulerian path, but not a circuit. Such a path starts at the one of the odd degree vertices and ends at another. This rule makes logic sense. The start vertex has one extra outgoing edge and the end vertex has one extra upcoming edge, while another vertex still have degrees. So the ending vertex is a final decision. using a one edge, and thus it's also need a total edge or degree. Case analysis summary. Remember, for any of these cases, the graph must be connected. If a graph is disconnected, meaning one vertex or edges are isolated, it cannot be Eulerian or semi-Eulerian. If there are 0 odd degrees vertices, Eulerian type of graph is Eulerian and result it contains an Eulerian circuit and path. If there are 2 odd degrees vertices, the graph type is semi-Eulerian, contains an Eulerian path but not a circuit. If there are more than 2, 4 or 6 or 8, the graph type is non-Eulerian. Result, it contains neither an Eulerian path nor a circuit. Note, the graph must be connected, ignoring any isolated vertices. A disconnected graph cannot be an Eulerian. Example, Eulerian circuit in C5. The it looks it looks like an example. Each vertex has a degree of 2 which is even. Since it is connected and all degrees are even. C5 is an Eulerian graph. One possible circuit is V1 to V2, V2 to V3, V3 to V4, V4 to V5, V5 to V1. Every edge is connected once. The conclusion is, since all vertices have an even degree, the graph is connected. It's an Eulerian. Example, semi-Eulerian path. If we take an path where two endpoints each have a degree of 3, meaning of odd degrees, and all others have even degrees, then the graph is semi-Eulerian. The path will start at the one of the odd degree vertices and ends at another, using every edge exactly once. Hezler algorithm. Algorithm comes for construction is. His algorithm is high efficiently method for finding Eulerian circuit and path. The core idea is to decompose the graph into edge disjoints and cycles and then merge them together. The steps are to start with at any edge v v0 or an odd degree vertices if finding a path. Find a circle of trace a closed trail C1 until return to V0, removing the edge as you go. Check if all edges are used. Stop at C1 is the Eulerian circuit. Splicing. If unused edge remain, find vertex V on C1 and is also connected to the unused edge. Repeat. Repeat to the start as new cycle C2 from V using only unused edges. Merge splice C2 into C1 at V. Repeat steps 3 and 6 until all edges are used. By repeating this process, we eventually cover all the edges and get the Eulerian path or circuit. This algorithm forms the basic of many routing algorithms used today. Applications of Eulerian graphs. Eulerian graph has fascinating real-world applications. They are the first one, the Chinese postman problem. It is very famous. Finding the shortest path that covers every road or street exactly once. If the route is Eulerian, the solution is simply the Eulerian circuit itself. If not, we add the fewest edges possible to make all vertices even. The second one is network optimization. It is very important to learn the network optimization because they help us in designing the efficient routes for garbage collection and snow plowing and mail delivery. Each where every each street need to be covered at least once. And computational biology. This also the graph theory is used in biology. For example, in DNA sequencing, Eulerian paths are used to reconstruct the sequence from overlapping fragments using a structure called deep graph. So from posture graph to the biology, Eulerian concepts play a vital role. Eulerian were Hamilton graphs. It is very important not to confuse Eulerian and Hamilton graphs. Eulerian circles cover every edge exactly once, while Hamilton circles cover every vertex exactly once. They deal with different transversal problems, but not the fundamental in, in network theory. Summary and conclusion. To wrap up, a graph is a Eulerian if all vertices have even degree. It's a Eulerian is a semi-Eulerian if exactly two vertices have odd degree. The concepts have solved optimization and transfer problem of efficiently. What started as a simple puzzle in Coensenberg became a cornerstone of graph theory and modern computation science. Thank you so much for listening.